Students, this is a beautiful comprehensive problem that kind of wraps together all of electrochemistry. They give us two half reactions at the top. They're both written reduction style, and we've got to choose one of them to flip because it's a galvanic cell, and as you know, galvanic cells have to have positive cell potentials. So we'll choose the one to flip so that when the voltage is flipped around and added to the other voltage, you still get a positive result. That means we'll flip the thallium reaction. We'll keep the gold reaction exactly as it's written. And if you look up on a table of they give it to you. The voltage is 1.5. And if we flip the thallium reaction around, we get thallium and 1 electron, and the voltage becomes a positive 0.34. To get the overall equation, we've got to make sure that the number of electrons crosses out. So we're going to triple coefficients in the thallium reaction, but leave everything else the same, including the voltage. It does not change. The electrons cross out, and we've got at the end gold ions. We've got solid thallium metal. We've got, on the product side, thallium ions and solid gold metal. And a total voltage under standard conditions of 1.84, which will be important. In part A, they just want us to list that. Formatting warning here. They want in the first box a coefficient, and then in the second box the formula, and luckily this time they give you the state of matter. There's no third box for state of matter. So they're calling for, at first, the aqueous species. So that means, okay, that's the gold. Don't put the thallium there because that's not the aqueous species. And you have to actually write out 1 for the coefficients. So AU, and then you can write 3 plus. And then in the next set of boxes, they're calling for the solid reactant. That's thallium metal. So we'll put a 3 and then TL for thallium. On the right side of the arrow, in the first set of boxes, they're calling for the solid species. That would be gold. So 1 AU, neutral. And then after that, the aqueous species, which is 3 thallium ions. Standard cell potential is what we found by adding together the two voltages for the half reactions. Okay, so that much hopefully wasn't too hard. In part B, they're going to ask us for the free energy change under standard conditions. To get that, we'll use what I think is a familiar equation. Negative N times F times the standard cell potential. N is the number of moles of electrons transferred. F is Faraday's constant. Which has a value of 96,485 coulombs of charge for every mole of electron. And then N, this is important not just for this part of the problem, but later on, the coefficient in front of the electrons just before it crosses out is a 3. That tells us how many moles of electrons were transferred in this reaction. And the standard cell potential is 1.84 volts. I'm going to list the volts as joules per coulombs, which is another way of writing volts, so that we can show coulombs crossing out. And if you pull out your calculator and crunch the number, we get negative, big number here, 532,597. This would be joules per mole. The per mole bit is not necessary to write, but it's often written. And WebAssign asks for the units of that answer to be in kilojoules, so let's divide by 1,000 and round to the nearest whole one, and we get negative 533 kilojoules, or if you want kilojoules per mole, but we would write negative 533 for delta G0, or delta G standard. Okay, next part. This is getting funner and funner, right, students? They're asking for the equilibrium constant K. Well, the only equation we have that includes the equilibrium constant is this one. Delta G standard equals negative RT ln K. And R is the universal gas constant. Which can be, in this case, it's in an energy. So if it's in an energy equation, you could either state it as 8.3145 joules per moles times degrees Kelvin, or, as will be more helpful for us, 0.00834145 kilojoules per moles times degrees Kelvin. So let's use the delta G standard that we had found in the earlier part, negative 533. We'll use negative 0.00834145 kilojoules per moles times degrees Kelvin. And, oh, and you might say, hey, what's the temperature here? The degrees sign, since we're talking about standard conditions, means that we're doing this under standard temperature. Standard temperature, standard conditions is 298 degrees Kelvin. And then natural log of the equilibrium constant K. And if we look at units that cross out, kilojoules goes away, degrees Kelvin goes away, and we're going to be left with a unitless equilibrium constant. Go ahead and pull out your calculator, and we'll find that the natural log of the equilibrium constant is equal to approximately 215. Well, how do we undo a natural log? We take e raised to both sides. That crosses out the natural log. So the equilibrium constant is going to be the number e raised to, this is quite a big exponent, 215th power. Go ahead and type that into your calculator. 2.36 times 10 to the 93rd. Whoa. Easy there, cowboy. Students, we're pushing the limits of your calculator here. 93rd power. If you think of a mole as a big number, this is this is way bigger than a mole. Okay. So we're talking big number here. All right, part C. We're talking about the Nernst equation. They're giving us, and we do have to return to the original formula here in a second, but we're going to use the Nernst equation to get the non-standard cell potentials. Non-standard cell potential is the standard cell potential minus 0.0591 over n times log log times q, or natural log base 10 of q. We know most of these numbers here. 1.84 is the standard cell potential. We looked at the two half reactions earlier and had determined that the number of moles of electrons transferred was 3, but we need q. Okay, let's go back up and find q. So if you look at the equation at the beginning, let's see. I'm going to rewrite it because it's hard to. Okay, now we've got this so that we can work and find Q. So I'm looking at the overall reaction, and if I were asked, okay, I need to write an expression for the reaction quotient Q, products over reactants, ignoring solid species, I would write, okay, thallium concentration, thallium ion concentration raised to the third power. The size of the charge is a 1 plus. That's what I was correcting there. All over the concentration of gold ions raised to the first power. They gave us, way up at the top, they gave us those numbers. They said the gold concentration is 7.7 times 10 to the negative second. That's my red number. And my thallium concentration is 1.7 times 10 to the negative fourth. Okay, so if I'm trying to find Q with that information, and I'm marking right here, I'm going to plug in 1.7 times 10 to the negative fourth, and I've got to cube that, and 7.7 times 10 to the negative second, and that's all to the first power. Crunch that number on your calculator, and you'll get, in my case, 8.3 times 10 to the negative 10th. So that's my value of Q. We're going to work with that, plug that into the Nernst equation. .3 times 10 to the negative 10th. And now we've got a nice Nernst equation that we can work with. Okay. All right, so 1.84 minus, got to crunch some numbers on the calculator here, 0.0591 over 3 times the log log of 8.3 times 10 to the negative 10th. Altogether, that's 0.18 volts. And if you put it all together, we get 2.02 volts as the final answer. This problem had you walk through all of the major equations of electrochemistry, and I think is a great way to study for that exam that's coming up.